So it should stop blinking and start recording, and yeah, there we go. So, plan of attack. First of all, I think at this point, I'm trying to remember, I have most, if not all, the exams back. My plan is to grade those over the weekend. I've just been setting stuff aside. So over the weekend, definitely by the time this class meets on Monday, I will provide you updated grades on Blackboard. Just so you know, I am going to be providing those updated grades to both our JCC folks here on campus, who kind of oversee the program, and I'm also going to be providing those updated grades to your contact people at your schools, because I know that your schools, while you're not quite at that point yet, your schools start to be interested in those types of grades, and a couple of your schools use them actual and grade computations and have requested actual averages. And so once I have those, I'll give you the most up-to-date average that we have for you. But I wanted to alert you, and you all sign a release anyway, and under educational law, because I'm doing it for educational reasons, I can provide them to your school no matter what. But I'd like to let you know that I'm going to provide that information off to your school. But what I will, and the way I typically do that, is I'll have them posted sometime before class on Monday, and then later in the day on Monday, I will actually send them off to your school so that you will have an opportunity to take a look at them prior to me sending them to your school, just so that you see them first. Does that make sense to everybody? Yeah, okay. Well, my whole big goal today is to finish off chapter 4. That's kind of my big goal, is to just finish talking about chapter 4. And what I want to do is talk quite a bit through some of the problems in chapter 4. So that's where I'm heading. And so what I'm going to do is I'm going to work through some questions in 4.4.4.5. We'll see where we get when we move on to, see if we can move on to 5.1, but I'd prefer to kind of wait to see if we get that far. So I'm going to work through a bunch of problems in section 4.4 to start. So let me convert my stuff over here. Document, camera, send. While that's doing that, I'm going to sharpen a pencil. So let's see, did it change over? It does not look like it changed over. Try it again. Some of this changeover bothers some of the other faculty more than it does me. I just kind of deal with it. So let's take a look. I'm going to just pick on a few questions. So I'm in 4.4. And what they're asking us is kind of what's the effective annual yield if a deposit of $1,000 grows to 3,500 in 15 years. Now, first thing to remember is kind of the formula that we're working with. And so the formula we're working with, and I'll use what they have, is the one that's actually right above, but I'm going to write it so I can move the paper. The balance equals P times 1 plus R over N to the NT. And remember, when I did this, I put the NT in parentheses so that we would remember. Now, this particular question gives us most of the information that's here, but there's one piece that it doesn't, there's a couple of things it doesn't give us. One is they're actually asking us about this annual yield, and you'll notice that when we look at this, they didn't give us a percent, and so that annual yield is actually the R that they're looking for. The other piece that they didn't tell us, and if you remember from the formula, the P, they call it the principal, but that's the actual, I'm going to call it the amount we invest. So they gave us that. The T is the number of years. They gave us that. We already said they didn't give us R. And they didn't necessarily give us n, but when they don't give us n, and that's the number of times per year we invest or compound, whatever we're doing, when they don't give us that, if they don't tell us the number of times, we're going to assume right now that n is 1. So if they don't tell you, we're really in an annual situation. They kind of led us to believe that and asked about the annual yield. But if they want us to know and want us to do something with that, what they will do is they'll tell us quarterly or daily type of setup. So let's put in what they know. What do we know? Well, we know it grows to 3,500 in 15 years. So that's the ending balance. They tell us we deposit 1,000. Again, I said they didn't give us n, so n is 1, so we really just have 1 plus r. And then they tell us 15 years, and again, because n is 1, that's just going to be a 15, and so we're just looking to solve this. So the way we'd solve this, I'm sure you're all really good at this. I divide by 1,000. Which gives me 3.5 is 1 plus r to the 15th. Is somebody's door open in one of the schools? Thanks. Now, what we have to be a little bit careful with is how we solve this. Last time that we met for a regular class, we talked about sometimes when we solve, we can use logs. This is not a log solving problem. And that's where we're going to be heading in the next chapter is the log solving. How do I tell, let's kind of ask this question. How do I tell whether a question is a log solving problem or not a log solving problem? Does anybody kind of know the sense of when you use logs and when you don't? Yeah, did you say the variable?
Yeah.
Yeah, what's true about the variable? You're right. You've hooked onto exactly the right point.
It has to be an exponent.
Yeah, if the variable's in the exponent, that's when we'd use logs. And I'd like to I like us to kind of chew on that for a while. If the variable is the exponent, that's what's going to take us to logs. If the variable is not in the exponent, then we won't use logs. That's really kind of a key idea that messes up a lot of students. So we won't use logs here, so instead if I want to solve this, what do I need to do instead of taking the log? Yeah, I'm going to take the root. The 15th root. So I'm going to take the 15th root of 3.5. And when I take the 15th root here, the root and the power cancel and I get 1 plus r. So r ends up becoming the 15th root of 3.5 minus 1. And we could put that in the calculator. I will remind you that you need to make sure you can put roots in your calculator. I have to confess that I don't use the root function on the calculator, but if you are going to use the root function on the calculator, remember to do this. What you would typically do is type in the number 15, and then you have to go to that math menu and catch the calculate part, and you're going to do the x root function, and I always put this in parentheses even though it may not be needed. If you're going to do the root, it's the root number first, then you have to go into the math key and do that calculate feature to get the xth root. I have to confess, and I've seen a couple of you do this on work, that if I want to do it, I always just do 3.5, and I have to do it in parentheses. I'm going to actually put it the way I put it in the calculator. I actually, when I want to do a root, I just do the 1 over that root power. It's fewer keystrokes usually. And again, the 3.5 this time, I didn't really need the parentheses on, but I do 3.5 and then the up caret to the 1 over whatever the root. So if it's the 15th root, it's 1/15. If it's the square root, it's 1/2. And so I tend to do that because more often than not, it requires fewer keystrokes. And then that would give us the work from there. So I wanted to do this question, one, because it brought us back to the formula, but two, it let me talk about when I use logs and when I don't use logs. And it also helped me remind you when you have to use, or how we do the roots with the calculator, because that's again something that often needs a little bit of familiarity for us. So a couple of other questions. I'm going to actually pick on question 11 here. Some of these I'm going to tell you are not my favorites, but I like to do them so I make sure that we hedge our bets as we move on through the course, because again, I don't know whether the math department's going to really be into this nominal and effective piece. Again, I'm not, but I try to make sure that we cover it. In exercise 11 to 14, what are the nominal and effective annual rates for an account paying the stated amount of interest compounded annually, quarterly, daily? So typically, I'm going to pick on 11. Typically, if you're not told otherwise, the rate that you're going to be given, the rate in these problems, is typically the overall nominal rate. So the rate that we're given, unless you are told the effective rate is, and notice here they said the stated annual interest. So typically, and the way I'm going to do the problems is this percent that you're given is going to be the nominal rate. The neat part is if you compound annually, the nominal and the effective are the same. So just so you know, when you hear this language, the nominal and the effective are the same if you compound one time per year. Where they become different is if you compound more than one time per year. So if we compound quarterly, what happens, and you're going to watch me pull off part of that formula that I used before. You're going to watch me pull off this part of the formula. Because if I'm just talking about the rates, if I'm not given any money, if I'm just talking about the rates, it's this part of the formula they're having me target in on. And so now what's happened is our N is changing. And that's going to change the interest that we have. Again, I said last time, the more times we compound, the better the interest rate is. And if we're earning money, that's what we want. We want more times to compound. If we're paying interest, if it's a loan, we really don't want them to compound more often, but they do anyhow. And so the nominal rate is in that formula what we typically call the R. And so in this case, it's 1%. Remember, we have to do this as a decimal. And notice on the quarterly, that means we're 4 times a year. And that means that our N is 4 in the exponent. And again, they didn't give us other years, so we're really looking at 1 year. That's supposed to be a multiplication symbol, not a decimal point. And so what's really happening now is I yank out my handy dandy calculator. And when I yank out my handy dandy calculator, I would do that math. And so parenthesis 1 plus 0.01 divided by 4. And then I'm going to raise that to the number 4. And if I do that, that gives me 1.01004. And now if I want to get the effective rate, for all practical purposes, and I want to be careful when I say this, but for all practical purposes, I ignore the 1. I don't really ignore the 1. What I really do to get the effective rate is I take 1 minus that. And when I do that, I get 0.01004, or in other words, I get 1.004%. That's my effective. If you're like I am, sometimes you look at this, you go, big deal. That's not much more than 1%. Who really cares? Well, if your loan isn't a huge loan, it probably makes next to no difference. If your loan is a huge loan, it starts to add up over time. Now, if I do it daily, it's the same process. 1 plus 0.01, and now I just have to deal with the daily. And this is always dicey because students go, is it 364? Is it 365? What do we use? Your book tends to use 364, I believe. Banks actually use 360. So I'm pretty flexible. As long as I see your work, whether you use 360, 364, 365, doesn't matter to me. So I'm going to use the bank numbers just because I like to be more like the bank. And so I'm going to do 1 plus 0.01 divided by 360. And again, I'm going to raise to the 360. It's just 1 year. And so if I do that, and I enter that in my calculator, again, I'm being consistent. You'll notice I get a slight difference. That's going to give me 1.01005. And again, if I subtract the 1 to get the effective, that's going to give me 0.01005, or in other words, 1.005%. So getting from nominal to effective is a formula, and that's why, quite frankly, I don't care for it as much. It's kind of like this formula piece, and this is a pre-calculus course, and so in a pre-calc course, I like to be thinking about things that are preparing us for calculus. You'll never see this in calculus. It's a nice little banking maths application exercise, which is always great. I didn't ask you to do this, but look at 18. I'm going to set 18 up. A sum of $850 is invested for 10 years, and the interest is compounded quarterly. There's $1,000. Let me widen this out a little bit here. There's $1,000 in the account at the end of 10 years. What's the nominal annual interest rate? So again, when they want the nominal, they want to know what R is. And so now it just becomes a plug in the information. And so they tell us 1,000 at the end of 10 years, invested at $850, 1 plus, we don't know R. What's N going to be this time? How often are we compounding? Quarterly. What's quarterly mean? Means 4. Yeah, 4 times a year. Raised to the, and remember it's NT, so N is 4 and it's 10 years, so it's raised to the 40. It's raised to 40. And now it becomes that same process we used before. Divide by the 850. I'm not going to do all the steps out here. But divide by the 850. Now, the exponent is a number, so we'll take the 40th root. And we'll solve for R. And that'll give us the nominal rate. So, I'll write that part of it down. We'll take the 40th root. And then to solve for R, I'm going to do the math fairly quickly and not actually do it out. Right? Subtract 1 from what I get, And then the last thing I do is multiply by 4. These problems don't get a heck of a lot more exciting than this. I want to look at 21, because 21 is kind of a neat little question. Suppose $3,000 was invested into one of 5 accounts, and T is time in years. For each verbal description, state which formula could represent it. So I wouldn't even look at the A, B, C, D, and E. I'd look and actually write the formulas. So first of all, $3,000 is invested. And so if I do write my formula out here, where does that 3,000 go? P, I think I heard somebody say. I on purpose used A and P so that I could understand what you were saying. So that's the only information that they gave me initially. Then they say the investment earns 12% per year compounded annually. So, compounded annually. What does, first of all, the 12%, where do I put that in? R, that's my R. What does the compounded annually tell me? Yeah, N is 1. So the formula becomes 3,000, 1 plus 0.12, and then raised to the, well, we said N is 1, so that's raised to the T. So clearly we can see, I guess I used B when they did it, so I'll change that to a B. So it's pretty clear that those two to go together. Now I'm going to skip the second one, because that's a little bit different. Let's go to the third one. The investment earned 12% per year, compounded twice annually. How does that change what I did in the first one? So if I'm looking at this one, how does that change my formula? N is 2. You're right. Very good. So B then is 3,000. 1 plus 0.12 over 2 raised to the 2t, which becomes that one. Now we have the rest of them, which are now this less and more and all of that. So let's jump into letter 2, letter II. This investment earned more than 1% each month. So first of all, there's a couple of things going on here. And by the way, notice that we have kind of some quarterly stuff going here. You know, we have some every 6 months stuff going here, and we have this piece. And so we want to figure out which investment earns more than 1% each month. What we might want to do is look to see over the course of a year, how much do each of these earn? So if I were going to do this one, oops, that's not one I want to look. If I'm going to look at one that's left, this 1.2, I'm just going to look at that part. If I look at that particular piece, and I look at it for the course of a year, The nice part is that's going to give me 1.2, right, if t is 1. It's going to give me 1.2. So that's going to tell me that I'm going to earn 20% in a year. If I convert that over, remember that 1.2, I take the 1 off, and so I'm going to earn 20% in a year. Well, that's kind of telling me that that probably matches up or could match up with this one right here, right? Because I'm going to earn 20% in a year, more than likely, I'm going to earn more than 1% in a month. Right? That kind of leads me into thinking that. I'm going to need one that earns less than 3% each quarter. Well, starts to lead me to believe, especially as I look at this one, this is the one that appears to be dealing with the quarter. And if I want to convert that, and this one's a little tricky, I know that if I'm dealing with quarterly, that I have to have 1 plus something over 4 to the 4t, and that 0.03 has to somehow divide out. So that looks like that's going to be 0.12 in order to make the math work. Right, so that's going to make, since this is kind of telling me I'm going to earn, when I look at this particular formula, this right here is actually telling me, if I looked at 1 year, I'm going to do the math out, 1.03 raised to, and I'm just going to raise it to the 4th power. That's going to give me 1.12551 for the whole year. All I did was this part of the math, by the way. Or in other words, 12.5% overall. 12.5% overall. That's going to indicate to me, if I kind of think of that, that's going to actually tell me I'm going to not get less than 3% each quarter, because if I divide this by 4, it's going to be more than 3. So if I divide this into quarterly, and just kind of take a rough by quarter, that's going to give me more than 3%. But notice if I divide it by 2, the 6-month period, if I divide it by 2, it's going to give me more than 6%. So this is a little tricky. I'm not a big fan of this question, but I knew it was going to give students trouble, give you guys trouble. So if I look at this quarterly, that's going to be a little bit more than 3%. If I look at it in a 6-month period, just by doing some random math there, some kind of quick math, that's going to give me a little bit more than 6%, and so those two would match. Again, not my goal to do this to you, but I dug out that question, said, oh, I know that one's going to give students trouble. And then by using kind of a similar argument, I'd look at the last one. They tried to trick us because of the 4s and the 2s and all of that. Not, again, my favorite question, but I wanted to get a little bit of the thinking. So what I did was I looked at each of these based upon, one was easy, but I looked at each of them based upon 1 year. So I actually did the math using a t as 1, and then I looked to match to see which statement makes the most sense. So you make t as 1, and then do kind of a quick, okay, if I do it twice annually, if I do it each quarter, if I do it, 6 months is the same as twice annually. Look to see which ones match. So what you want to do is put the t as 1 in any one that you can't just directly get the formula, and then do some quick math and make your decisions. Again, not my goal to do that to you, but I'd like to make sure that that's kind of a goofy one that you've taken a look at it. So I don't want to belabor that section. it really is a lot of formula. It's really a lot of just effective versus nominal. Because what I'd like to do is I'd like to spend about half an hour here talking about section 4.5. And I need to ask you a little question. How familiar are we with E? So, Alex Bay, have you used E in your previous math classes? Yeah, okay. Copenhagen? They're all, yeah, maybe. I'm not getting a warm fuzzy that we all feel really excited about it though. Sackett's. Yeah, okay. You sounded the most enthusiastic of the group. So, E is actually an irrational number, right? Remember, irrational numbers are numbers that have a decimal approximation that go on forever and have no predicted repetition. Pi is another irrational number. E is an irrational number. It was actually introduced, in case you didn't know it, by a mathematician by the name of Euler. I know his name looks like Euler, and he was a Swiss mathematician. You notice that basically we're looking at E as Euler's number, and that's why we see the E written there. It's not because somebody's like, oh, we haven't used that letter of the alphabet. Actually is often called Euler's number. Part of what Euler was doing was he was actually messing around with looking at this formula. He was looking at, in the parentheses, 1 plus 1 over n raised to the n. Right? That was one of the formulas he was looking at. And so if I made n be 1, what ends up happening is I have 1 plus 1 is 2, 2 to the 1 is 2. So he actually started playing with it. So he did n is 1. When he did n is 2, we ended up having 1 plus 1 half raised to the 2, and that gave 2.25. And then when we did n is 3, it'd have 1 plus 1 divided by 3 raised to the third. That gave, I'm going to do a few of these, 2.37037, and so on. I'm going to cheat and go right up to 10. And so if we did 1 plus 1 divided by 10 raised to the 10th, we're at 2.59374. If I go all the way up to 100, what Euler noticed was that gives us 2.70481. And if we kind of kept going over and over and over again, what we would actually find is that this would get approximately 2.71828, and then a pattern that doesn't repeat. And so Euler was messing around with that, and he noticed that the larger the n went, and using some of our previous notation, if we did the limit as n goes to infinity of 1 plus 1 over n to the n, that gets us to approximately, or gets us to, as we're going, this 2.71828. And that then, he said, was, or we then credited as this item E. E actually operates, and notice when we look at this, remember our formula from the previous section? I'll go back to the B. If I ignore the R for a moment, or if I were to make the R be 1, notice we start to see that formula come out. And that's, as n becomes infinite, that's as if I'm compounding money, or compounding a population, or compounding what have you, continuously, every second, every microsecond. every tiny, tiny, tiny fraction of time. And as we know in the real world, populations don't just grow. We don't just go, oh, yep, it's the first of the year, all the babies are born. No, babies are born all the time. Decay, in terms of radioactive decay, happens continuously. And so this became kind of the formula, or became the piece, for what we would call continuous growth or continuous decay. And we use this E whenever we have continuous growth or continuous decay. And so I'm going to do a little hand waving here, but then what happens is our formula that we had before, where we had y equals a times b to the t, actually then becomes this b actually gets replaced in terms of the continuous decay. And what Euler realized was, if we're decaying or growing continuously, the continuous factor converts that b into an e to the k. So Euler recognized that the old b we were using was really much related to annual growth. And if I wanted to do something that wasn't annual, if I wanted to do it continuously, the corresponding continuous number would make b be e to the k. I'm leaving out a lot of the details. So, notice something here, that what we are now going to do when we have continuous, and by the way, the math teacher tries to be as obvious as we can. If you see the word continuous in a problem, we're going to be using that formula, or some derivation of it. You know, the letters might be slightly different, but Q equals AE to the KT. If we see the word continuous, we're going to use that. Some of you, since you said you've done E before, some of you probably learned it as either cert or pert. I tend to remember it as either cert or pert, not AE to the KT myself, because I learned it as cert and pert. Same formula, just different letters. The thing that's important to recognize, and the part that gives people trouble, and I'm pulling this out of your notes or out of your book, is if the exponent is positive, then we have growth. If the exponent is negative, we have decay. So I'm going to flip my page over because I want to because this confuses people, always confuses students. So if we're dealing with annual growth or decay, that was our formula where we had y equals AB to the t. And what happened here was, if b is between 0 and 1, we had decay, and if b was greater than 1, we had growth. But notice, b is always greater than 0 in that formula. So in the annual situation, b is always going to be greater than 0. If it's between 0 and 1, we have decay. If it's greater than 1, we have growth. If we're in the continuous situation, and I'm going to use my old friend cert just because I tend to like it. And students tend to remember cert or pert better. In this case, we're going to have R, and if R is greater than 0, we have growth, and if R is less than 0, we have decay. So notice, R here can be positive or negative. So in the continuous situation, we might have a negative exponent. In the annual situation, we will not have a negative b. And so if I kind of compare the b's and the r's together, So we have to be a little careful with what we're doing. So these are the two formulas that through this chapter are really important. The only other one we add to it is that compounding formula. And I'm just going to write that one down just so that we have it. B is P 1 plus R over N to the NT. I mean, those right there kind of summarize most of the chapter in terms of the big exponential formulas. So, I want to look at a few problems because, again, I gave you videos you can follow through in terms of some notes. So I'm digging my way out to some problems here. And I want to get to some of them that are much more exciting. I want to look at question 3. Without a calculator, they want us to match each formula to the graph. Well, let's take a look here. There's the E portion. Notice in these two cases, they're negative, where the exponent's negative. So those two tell me it's growth or decay?
Okay.
Decay. So if I look at the pictures with items 1, 2, 3, and 4, those two have to match to which two? And I don't care if I get the right order. 3 and 4. So these have to be either 3 or 4. What is my rate of decay here? What percent?
1%.
That's a 1% decay. And what's my rate of decay here? 10%. Yeah, you're right, 10%. By the way, continuous is actually easier, I think, than annual because it's kind of what you see is what you get. There's none of this adding one, subtracting one mess. So now if I look at these two graphs, which one do you think decays by 1% and which one do you think decays by 10%? So let's pick the 1%. Which one do you think decays by 1% and it's continuous? 3. Why do you say 3?
Because it's not decreasing as fast.
You got it, because it's not decreasing as fast. And so this one here must be the 10%. It's decreasing more rapidly. So the other two are the increasing ones. What's my rate of growth, my continuous rate of growth on B? 5%, you're right. And my growth rate here is 20%, you're right. And so now if I look at the two pictures, which one do you suppose is 1? Which percentage? Yeah, the 20. And then the other one must be the 5%. So this one must go with B, and this one must go with D. So without even using my calculator. Now, I'm not naive enough to think that, oh, if I gave that to you on a homework assignment or an exam, that you wouldn't pop it in your calculator, but at least hopefully we all kind of understand why. So now I want to look at some of the word problems. We're heading toward the word problems. So I want to take a look at these questions. I'm going to look at 9. The expression shows how a quantity Q is changing. And I want us to say, what's the quantity at time 0? Is it increasing or decreasing? What's the percentage per unit growth or decay rate? Is the growth continuous? So actually, let's look at 8 first. I know that 8's is an even question. I don't typically ask the even ones. But let's run through 8. So part A, what's the quantity at time t equals 0? So what do we think at Alex Bay? What's the quantity at time t equals 0 at number 8? 50. You got it. So, Copenhagen. Is the quantity increasing or decreasing over time? Increasing, why? Exponent's positive. 1.05 is positive. Seconds. Now this one's tricky. Okay? So if we don't get this right, don't panic. But what is the percent per unit growth rate? And this one's tricky. Trying to be tricky here. So what's your first thought? You're never very noisy, so I have to have you yell at me almost. And there's only a couple of
You
people.
would think 5%, but if it's tricky, we don't have.
Yeah, it's not. You'd think it's 5%, and it's not. You're right. That's you know what when I said it's tricky, you knew which one not to say. So here's the cool part: when you have an E, in a lot of ways, what you see is the R as a decimal. So it's not 5%. What it actually is that the R is 1.05, which as a percent is what then? Anybody want to help them out? Because I know that they're at a severe disadvantage. They're much smaller a group. Okay. Yeah, it ends up being 105%. So we don't do that 1 plus R, 1 minus R with the E. The exponent actually is the R, and when we just convert it to a percent. That's tricky, isn't it? And then the growth rate is continuous because of the E. Let's skip 9 for a second. Let's go break down to 10 right now. So let's run through this pretty quickly. Part A, what's the initial value? Or time at 0. Value at time 0. 0.01. Are we increasing or decreasing over time? Decreasing. What is the percent that we're decreasing? 20%. You're right. R is, I'm not going to use the negative, but R is 0.2, and then we convert that to a decimal, or to a percent, I should say. That's 20%. And then again, it's continuous because we have the E. Let's go back to 9. I knew it'd be important to do a couple of these. So now if we go to 9, what's the amount of the quantity at time 0? 2.7, you got it. This is the different formula, there's no E. So are we increasing or decreasing over time? Decreasing. How do we know we're decreasing? It's less than 1. The B is between 0 and 1, right? Because this formula is actually written in the form A times B to the T. Now, again, remember with the B's, this is a little trickier. Let's do this in 2 stages. What is the R as a decimal? You got it, 0.88. Remember, our R in that case is how far we are from the number 1. And so to get to the number 1, we'd have to go another 0.88. And so as a percent, we'd be at 88%. And so notice, because it's decay, B is 1 minus R, so 0.88 is 1 minus R, so R ends up being 1 minus, not 0.88. use the number that they gave me, 0.12. So R is 1 minus 0.12, and that's where the 0.88 came from. So for those of you like, how'd you get that? We're in decay, and so the decay relationship is B is 1 minus R, so I just stuck that B in they gave me and solved for the R. So in the decay, that's the process. It's a little bit harder than the other situation. And this one's not continuous. Let's just quickly look at 11. Initial value is 158, you're right. Growth or decay? Growth, yeah. Now in this case, notice that my B is 1.137. So what does that make my R? Yeah, 0.137 I heard a mumble of, which means as a percent, that's 13.7%. So notice how we operate differently, and that one is not the continuous growth, that's the annual growth. And again, the way we got this is in growth, B is 1 plus R, the B they gave us is 1.137, so R has to be 1.137 minus 1, and that's where we get the R value. It's important to be able to tell the difference. Notice on 15, 16, 17, they want us to write two formulas. They want us to write the not continuous formula, and they want us to write the continuous formula. So the not continuous formula, and they're having us write it as a Q, is A times B to the T. The continuous one is Q equals AE, and I'm going to use RT. I could use PERT or CERT if I wanted to. But I just use those and plug in the information that they gave me. Remembering that that number they gave me is always the R. And if it's continuous growth, I have to determine whether it's a positive R or a negative R. And if it's not continuous, then I have to do the 1 plus or the 1 minus. Right? So these questions here, with a little bit of practice, they should be easy questions. You should be able to write pretty quickly what the formulas are. And be able to tell the one formula from the other formula. And that's really what the rest of the section starts doing. Now if I look at a question like 21, and this right here, this is one of my favorites, and then I'm going to shut up here because I'm just about out of time. A population is 25,000 and year t equals 0, grows at, and notice the word, continuous rate. Notice, by the way, it also grows. So they want me to find the formula. This is how quickly you should be able to do the problem. P equals the initial population, 25,000. It's continuous, so it's E. There's my rate. It's growing, so it's positive, 0.075. T. There's the formula. You should be able to do that just about as quickly as I did it. Then the part B, I just want to kind of talk to this, is by what percent does the population increase each year? To figure out the yearly, you actually do the E raised to that number, and that'll actually give you the yearly percent. It'll give you a 1 point something or other, or a 2 point something or other. It'll give you, and you have to kind of figure out what the annual is compared to that. But that right there is leading you into the yearly value. And we'll see that. We have a section in in the next chapter where they do this all over again. In this one, it's really, I want you to be able to write the formulas. If you can write the formulas and do some simple computations, you're right where I want you to be. So let's quit here. And so what I'm gonna do is I'm gonna talk a little bit on Monday. We're gonna talk through 5.1 and 5.2. So make sure you've gone out and taken a look at 5.1 and 5.2. And for all practical purposes, you probably noticed this pattern that when I ask you to do problems from the book, I'm pretty much asking you to do most of the odd questions. So really, you just want to be chomping through the odd questions. And go through a few more odd questions, and if you have questions on them, don't hesitate to let me know. I will be posting, and it won't be due until Wednesday, I'll be posting a collected assignment, and I will be posting a little bit more Wiley Plus, another section or two. That'll be for Wednesday night. So don't panic if you go, oh, she hasn't given us anything new to do. I wanted to be able to meet with you today and kind of figure out where I was before I had you actually give you some more sections of Wiley and some homework. So have a great day, have a great weekend, and I'll see you all on Monday.
Every answer